Hello everyone, I'm Jiayu. I'm going to introduce our work, Cost-Volume Pyramid-Based Depth Inference for Multiview Stereo. This is a joint work with Wei, Jose, and Miao Miao. Multiview Stereo aims to reconstruct the 3D model of a scene from multiview images. It is a fundamental problem for computer vision and has many applications such as 3D reconstruction and virtual reality. Recent learning-based MVS methods build cost volume on the reference camera frustum for depth inference. Each voxel of the cost volume is the matching cost of corresponding features projected from reference view and all source views. The key insight of this method is the photometric consistency, which means that projected points of a same 3D point on each view should have similar appearance. For high-accuracy depth estimation, cost-volume-based methods typically inference on high-resolution images and sample depth hypotheses densely across the whole depth range, which leads to large GPU memory consumption. Another method tries to address this problem by sequentially processing the cost volume using recurrent networks. It reduces the memory usage but consumes much more time. Alternatively, Chen and co-authors try to first estimate a coarse depth map and then perform edge convolution directly on point cloud to refine the depth map. Despite its good performance, convolution on point cloud is not very time efficient as well. To provide a computational efficient MVS network, we proposed the CVP-MVSNet. It is fast, compact, flexible, and can produce high-accuracy depth estimation. Given a coarse depth estimation, it is not necessary to search the whole depth range, since the ground truth depth usually located around the coarse depth estimation. Inspired by works on optical flow estimation, the depth search range that may cover ground truth depths can be determined by a certain pixel distance along the epipolar line on source views. When it comes to search interval, which is the minimum search units, densely sample across the search range will result in large cost volume and very close pixel locations on source views that provides hardly distinguishable feature information. Instead, we project the proper sampled feature points back to 3D to form a local search range near the estimated coarse depths. To get a coarse depth estimation, we firstly search coarsely on the whole depth range using a cost volume in very small spatial resolution. For each iteration afterwards, we increase the spatial resolution and build a partial cost volume, and the depth search range well centered around the previous estimated depth with a smaller searching interval, and thus produce a more accurate depth map. Building a cost volume pyramid in this way will consume less GPU memory and is also faster on runtime. Combine all of these, let me introduce the general structure of the cost volume pyramid-based MVS network, CVP-MVSNet. Given a set of input images, we build an image pyramid and use a shared weight feature extraction network to extract feature maps for each level of the pyramid. Then, a small cost volume is built to estimate a coarse depth map. The initial depth map is then upsampled to match higher resolution image. And we build a partial cost volume to estimate a refined depth map. The refinement can be performed several times to generate high-quality point cloud. The network is trained on the DTU training dataset and evaluated on both DTU and tanks and tempos dataset. We first compare overall performance, the memory usage, and runtime with other methods on DTU dataset. Ours is much faster and smaller than other methods to obtain similar performance, and we can achieve best reconstruction results with shortest time. We also provide qualitative results on DTU dataset. On tanks and tempos dataset, we have also achieved good results. Our code is publicly available on GitHub. Thank you.